All right, this is Tuesday, December 15th, 2020, Physics CP course debrief on a homework assignment called Energy and Momentum Homework. This already has been recorded yesterday with a different period and posted up on YouTube, but I thought I would go through it again second time today, maybe getting it twice without just hitting the replay button will be useful for some reason. All right, so the assignment begins with problem 1, and these students are current students when I wrote these problems. Javin pushes on a 50.0 kilogram box to give it an initial velocity of 2.50 meters per second at the top of a roller coaster hill. The box slides down a 7.20 meter long ramp to the level ground 2.50 meters below Javin. Total energy, or part A, what is the total energy of the box at the top of the hill just after Javin finishes pushing on it? Katie, do you want me to solve this with the original values, or for some variety, do you want me to change some of the numbers? Okay. Yeah, I got it. And all right, and I see we have one student who is a little tardy. Got you. You're now updated for my records. So this is going to be the original values. I am doing a sketch. And by convention, the initial direction of motion in a physics problem is to the right, unless otherwise indicated. So I'm going to show this 50.0 kilogram block as sliding down and to the right. It's not a law of physics, it's just an agreement around the world. We don't know the angle, but what we do know is enough information that we could calculate it if we cared. And today we do not care. The height of this box was initially 2.50 meters. It's given an initial velocity of 2.50 meters per second. And it slides a distance along the hill of 7.20 meters. Okay. So I'm going to make a change so that you students can see the paper that I'm writing on. I was hoping that just by recording it, that would take care of it as well. All right, so here's the handout that was assigned, and here's the beginning of solving problem 1. So as I read the problem carefully, I then started to construct a sketch of what the information is telling me. Here's a 50.0 kilogram mass at a elevation of 2.50 meters for a hill that has a length of 7.20 meters. I give it an initial push at the top, or Javin does, of 2.50 meters per second. And part A, the question is, so what is the total energy at the beginning of this problem, which is right after it is given a push? Total energy is the sum of all the different forms of energy. So I'm going to make this a little more complete and thorough than I did yesterday, and make the claim that, well, all the different forms of energy. So there could be kinetic energy. There could be gravitational potential energy. And I know in high school we like to write it as PE, but I like doing it college style and call it capital U sub G. In addition, if there were a spring, the energy could be there as well. And if there's friction, then there could also be internal energy. Each one of these forms of energy has an equation that goes with it. Kinetic energy is 1/2 times mass times velocity squared. Gravitational potential energy is mass times gravity times the height. And maybe I should remind you a little bit. All right, so mass can never be negative. Velocity can be negative, but when you square it, it becomes positive. So kinetic energy can never be negative. The lowest value it can have would be for an object that's not moving, and that would be 0. For gravitational potential energy, it depends on where you choose your 0 height to be located. If you make 0 height at the bottom of this hill, then everything above that is positive gravitational potential energy. If you arbitrarily pick the top of the hill to be your 0 reference height, then everything below that will indeed be negative gravitational potential energy. If there were a spring present, then its formula would be 1/2 times k times x squared, where k is called the spring constant, how much force it takes to stretch it per meter, force per meter. And x is the amount that the spring is stretched or compressed from its rest length. Although this can be negative as well, it's squared. And so once again, the energy stored in the spring can never be negative. It could be 0, it can be greater than 0, but it can't be negative. And finally, internal energy is something that happens when we have friction. It is the result of friction doing work trying to stop something from moving. So if I take my hand and my other hand and I put them together and I start rubbing them one against the other, friction is constantly trying to stop them from sliding one against the other. In fact, it is doing negative work. If it did positive work, it would be trying to make my hands move faster and faster. But it's trying to stop them from moving. So mathematically, we say, oh, it's doing negative work. Well, how do we account for that in a physics problem? The answer is I consider it the negative of the negative work done by friction. And I'll embellish that in a little bit, like when we get down to around part D or so. But for now, the work done by friction is a negative number. Oh, friction did negative 10 joules of work trying to stop my hands from sliding against each other, for example. Internal energy is a positive number that represents how much increase there is in heat energy. So by rubbing my hands against each other, they feel warmer now. That's because of friction. So the internal energy is, for record keeping, a positive quantity that would go into our total. As problem 1 begins in part A, it says there's no friction, there's no spring, so therefore the total energy is just 2 things. Kinetic energy, because it's moving at first, and gravitational potential energy, because I'm going to choose to say the bottom of the hill is my 0 meter point. All right, so calculate away. E.T., which was my dad, yes, I'm the son of E.T., is the sum of kinetic energy and gravitational potential energy. In this case, 1/2 times 50.0 kilograms times an initial velocity of 2.50 meters per second, quantity squared. Add to that gravitational potential energy, 50 kilograms, times the acceleration due to gravity here on Earth, 9.80 meters per second squared, times its elevation above the 0 reference point. I'm just going to put all that into the calculator in one shot. So I get 1,300 Yeah, I'll call it 81 joules for now. Really, to 3 sig figs, I should round that off to 1380 joules. Of total energy. If you students have questions, you can unmute, or if your mic's not working, you can type it in the chat. If I don't notice it, then then Jonathan Hernandez will unmute his mic and get my attention somehow. Okay. There's part A. Part B. If there were friction, I'm sorry. Part B. If there were no friction, what would be the speed of the box at the bottom of the hill? So I look at this problem, and one of the principles of this physics problem in this universe is that we say that energy is conserved. It can't leave the universe, it can't enter the universe. And when we work on a physics problem like this, the total energy at the beginning of this physics problem must be equal to the total energy at all moments, including at the end of this physics problem. Well, I just calculated that the total energy is 1,380 joules. At the bottom of the incline, it could be in any combination of these four forms. Kinetic energy, yep. Gravitational potential energy, could be, but the height is 0, so that's going to be 0. Spring energy, could be, but there's no spring, so that's 0. Internal energy, could be, but in part B they say there's no friction, so that is 0. Therefore, at the bottom of this hill, all of the energy is now transformed into kinetic energy. So for part B, the total energy is exclusively in the form of kinetic energy. The formula is 1/2 mv squared. And what I can do is I can now rearrange this equation to solve for the speed at the bottom of the hill. I have to multiply both sides by 2. Divide both sides by the mass. Then take the square root to get the speed at last. So the speed becomes the square root of 2 times, and I'll even list it as total energy instead of kinetic energy, because they're the same value right now. So 2 times the total energy divided by the mass. So I'm taking the square root of 2 times 1381 joules divided by 50.0 kilograms. Powering up my calculator. Doot, 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 beep, beep, beep. And it displays 7.43 meters per second. That is my value for the speed at the bottom of the hill. Keep in mind, this is supposed to be slightly interactive. If all I do is just talk and present with no questions from students, this could have been an asynchronous class just pre-recorded. You could make it seem interactive by posing questions as we go along. Part C. There is friction, and the speed of the box at the bottom of the hill is measured to be 5.70 meters per second. How much of the total energy was converted into internal energy? Okay, so looking at the drawing, I'm going to draw a squiggle line, and that means there's friction all the way down this line, including the bottom of the box. If I ask you in a test question, so what heats up? You should tell me the surface of the ramp and the bottom of the box. Just like both hands heat up when I rub them against each other. Both surfaces gain internal energy. They both heat up. What they're telling us now is at the bottom of this ramp, when the box finally gets here, we observe that its speed is a measly stinking 5.70 meters per second because there's friction, instead of the 7.43 meters per second that we would expect if there were no friction. So here we go. Part C. The total energy can exist in any combination of these four forms. At the bottom of the hill, it has some kinetic energy, but not as much as before. At the bottom of the hill, it has zero gravitational potential energy. It has zero energy in a spring because there are no springs in this problem. There is friction, so it has internal energy. All right, well, the conservation of energy says all the energy present at the beginning of the problem, 1,380 joules, is equal to the sum of all the energy at any point in the problem. What I can do is calculate how much kinetic energy do I have if this 50 kilogram mass is only going at 5.70 meters per second instead of 7.43. Beep, beep, beep. And my calculator says 812 joules. That's how much kinetic energy I have at the bottom of this hill when I'm moving at just 5.70 meters per second squared. So I'm going to put that in here into this little placeholder for kinetic energy at the J. All the rest of the energy is in the form of internal energy. And in part C, this is what they are asking for. How much energy is now in the form of internal energy? You should recognize this as a Math 1 level problem, where if we subtract 812 joules from both sides of the equation, we'll have the answer to part C. I get 569 joules. Getting so old, I'm going to confirm that with a calculator. Oh boy, I did it correctly. Party time. Well, part D time, anyways. So what was the force of friction that was assumed constant on the box as it slid down the hill? So, you know when I mentioned that internal energy is the negative of the work done by friction trying to stop an object from moving? Now it's time for me to get into this in a little bit more detail. Work is defined in physics as the product of force dot displacement. Work is force dot displacement. So what is that mathematically? That means the magnitude of the force times the magnitude of the displacement, if it's not friction, distance, if it is friction, times the cosine of the angle. And what angle, you ask? Theta is the angle between F and delta x. And in the future, I really should have written it.
Can you zoom out a little bit?
Repeat your question, please.
Can you zoom out a little bit, please, so I can see more of the paper?
Oh, Prashant, I could just slide the paper. I can see all of it. I don't see what your problem is. Oh, you don't get my humor this morning. All right. I've zoomed out for a moment. And I'm trying to actually display almost the entire page so far in one shot. Those of you who love doing screenshots. Not sure which part you want me to focus on. I'm going to actually come back in on this now and address this part a little bit more and say, okay, what's going on? By the way, do you want me to present? Does that help at all? If I hit the present button?
I think it's fine like that.
Good, because I don't see how it's doing any good. All right. Back to explaining about work. So work I could represent with the symbol capital W. Don't confuse that with West, or later on the units of power, which are called watts, or in chemistry class, tungsten, or weight, which is the force of gravity. Yikes. Out of all those possibilities, W for work is F dot delta X, is the way I would write it normally. And the angle is between the direction of the force and the direction that it moves. A reminder that if they're in the same direction, the cosine of 0 degrees is 1. Imagine that that's the number 1, badly written. If they are perpendicular to each other, then no work is done because the cosine of 90 degrees is 0. If they are in the opposite direction to each other, then the cosine of 180 degrees is -1, and negative work is done. This explains why we say friction does negative work for objects that are moving. The definition of friction is friction always points opposite, and that means theta equals 180 degrees to actual or attempted motion, and that means delta x, the direction of delta x. Therefore, the work done by friction is the magnitude of the force of friction times the magnitude of the distance that you travel. I'm going to still write delta x, but it's the total distance. And so here's what I mean. If the box moves to the right and then back to the left, we would say its displacement is 0. But if it travels to the right delta x, that's a distance of delta x. And if it travels back to 0, friction reverses direction as the direction of delta x reverses direction. So it's really 2 delta x is the total distance traveled. So what goes into here when we're calculating friction isn't really displacement, it's really the total distance traveled. For any other force, we don't care about how it gets from point A to point B. We only care about the change final position minus initial position, so delta x. So maybe for clarity, I should say the work done by friction is the force of friction times the total distance d that it travels times the cosine of 180 degrees. In this problem, the work done by friction, the negative of the work done by friction is the internal energy. Okay, what is the distance in this problem? And the answer is that's the length of the hill, ramp, or incline, however I refer to it, that the box slid in this problem. And that value is 7.20 meters. We're getting somewhere. 569 joules of internal energy is equal to the force of friction times 7.20 meters. And if you want to be strict about it, friction will be a negative quantity. So I get the force of friction is, the minus sign means it's pointing up the hill, opposite the direction of motion. 569 divided by 7.2 is, beep, beep, beep. I get 79.0 newtons. This ends problem 1. All right, so an interesting question was posed by a student about when is friction positive, when is it negative? And I wanted to create an example problem. This represents a wall. Here is a box, and I am going to hold it up by pushing upward on this box. So I'm exerting a force by my hand, but I'm letting the box nonetheless slide down the surface of the wall. So the box is actually moving downward, even though I'm pushing up on the bottom of it. I'm not pushing up with enough force to even hold it up. I'm only pushing up with enough force to keep it from falling faster downwards. So in this problem, given that work is F dot displacement, the work done by me, and I'll call that A for applied force, would be negative, because while I'm pushing up on the box, it's actually moving downwards. The work done by gravity, so again, think of a free body diagram for a moment. The force of gravity is always acting down towards the center of the earth. In this case, the box is actually moving down. The angle between down and down is 0 degrees. The cosine of 0 degrees is +1. So the work done by gravity is a positive number. Now, what about friction? Friction always opposes the direction of motion. So if the box is sliding down, then friction is pointing up. And the work done by friction is negative, as it always is. That was a great question from a student. I hope this clears it up a little bit. I guess I could do the same wall, with the same box with friction and push it so that it actually moves up. Just for clarity, this is okay. My applied force is up, and I'm actually pushing the box up along the wall. In that case, the applied work is positive because the angle between up and up is 0 degrees. The work done by gravity is negative because gravity is always pointing vertically down towards the center of the earth, but the box is sliding upward. So the work done by gravity is negative. And finally, friction always opposes the direction of motion. If the box is moving up, then friction is pointing down, and the work done by friction will be negative. I am now going to launch problem 2 from this homework assignment. Starting from rest, Jessica pushes on her little sister on a swing at the playground. Her sister weighs 328 newtons. Jessica pushes horizontally on her sister with a force of 200 newtons for a time of 930 milliseconds. The length of the swing is 3.00 meters. Part A, what maximum height, and I know I wrote down, but that's a typo. I should have asked does. What maximum height does Jessica's little sister reach after one push, ignoring friction? I didn't have you do problems like this one before, so it's understandable if this one was a little too challenging to figure out. I have a swing. Oh man, and I can't draw a circle very well. But imagine that this is a circle and that that's the bottom of the circle, and that this swing has a length of 3.00 meters, that the little sister is sitting on the swing and she weighs 328 newtons. Okay, so that means that's the product of her mass times the acceleration due to gravity. It's not her mass that was given, it's her weight that was given. She was given a push by her sister, and I'm just going to show that as an applied force of 200 newtons for a time duration of 930 milliseconds. And the question became, so what's the maximum height that she reaches after that first push? So, yikes. To do this problem, I would use the impulse momentum theorem. Impulse with an E. Impulse momentum theorem. Really badly written. Impulse is average force times time. Momentum is really change in momentum. Mass times change in velocity, as long as the mass is constant. The applied force is Jessica's 200 newtons. The time is the 930 milliseconds. Now, milliseconds means 0.930 seconds, because milli means 1/1000th. To convert from milliseconds to seconds, you move the decimal point 3 places to the left. You divide by 1,000. I need the mass of her little sister. Her weight is 328 newtons. If I divide that by G, I will get the mass of little sister. 328 divided by 9.8, enter. Beep, beep, beep. And it says 33.46938,776, which means 33.5 kilograms. I now have 3 givens, and I can solve for the change in her velocity. Well, change in velocity is final velocity minus initial velocity. Her initial velocity was 0. So really, we're answering part A. Well, we're on our way to answering part A if we calculate what her speed was. Part A asks, what maximum height did she reach after one push? So I have to do it this way. I'm going to calculate what her velocity was. 200 newtons times 0.930 seconds equals 33.5 kilograms times her speed after this push. I hope you can all see that I'm going to multiply, and then divide both sides by 33.5 kilograms. So I multiply 200 by 0.930. I then divide everything by 33.5 kilograms, and I get a final speed of 5.55 meters per second. Now I can use conservation of energy. All the energy present is the sum of the kinetic energy and the gravitational potential energy and the energy stored in the spring and the internal energy due to friction trying to stop things from moving. We're ignoring friction, and there is no spring. So if I calculate her kinetic energy at the bottom of the swing and take the bottom of the swing to be 0 height, I'll have her total energy. All right, well, KE equals 1/2 mv squared. I'm going to plug in 0.5 times 33.5 times 5.55 squared. Not sure if I should bother writing that out. 1/2 times the mass times her speed after one push squared. Beep, beep, beep. I get 516 joules. This still doesn't answer the question. The question was, well, how high does she rise at the end of this first push? What is her height above the lowest point? My claim is, as the swing rises, the kinetic energy is transformed into gravitational potential energy. Sort of the opposite of that ostrich egg as we began this unit. The ostrich egg started at the top of the cliff with all of its energy, potential energy, and as it fell down, that potential energy transformed into kinetic energy. Here, Jessica's little sister is beginning with everything as kinetic energy, and when she gets as high as she's going to go, she will stop for a moment. At that moment, her kinetic energy will be 0. And all of her energy will be UG, gravitational potential energy. So if I take this kinetic energy of 516 joules, which is her total energy, and I set that equal to her gravitational potential energy, given by mg times h, where mg is given to us, that's her weight, I can now solve for the height that she reaches. The height that she reaches is going to be 516 joules divided by her weight of 328 newtons. Beep, beep, beep. She reaches a final height of 1.57 meters. A year ago, we had done physics problems like this. This year we did not. So it is forgivable if you had difficulty with this problem. Yep.
Isn't it 406? How do you get 516?
I think I multiplied 0.5 times 33.5 times 5.55.
That's what I got 506.
I may have to fail you. 0.5 times 33.5 times 5.55 squared. I think you need to check the batteries on your calculator, young man.
Oh, it's really another 5.
Good help. So hard to find these days. Okay, now I'm going to deviate from the questions on the handout and share with you one more idea. Here is my length of 3.00 meters. After she rises, so what is this? 1, 2, 3, 4, 5, 6 lines on my graph paper. After she rises by 1.57 meters, she's really going to be here. And this is all part of some huge circle, right? I could have asked you, what is the angle that her swing will make with the vertical? Here's how you would solve that trig question. The circle radius is 3 meters. That's the distance from the middle of the circle to the bottom of the swing. And although I drew it badly, it is also the distance from the center of the circle to the swing here, where she stops going up. The height that she reached, we know, is 1.57 meters because we just finished part A. This means we can solve for, I'll call it y, the difference between 3 meters, the full length of this, and her height above the ground, 1.57 meters. So if I go 3 minus 1.57, beep, 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 it says this little length there is 1.43 meters. The hypotenuse is 3 meters. This forms a right triangle where I know the adjacent side now, and I know the hypotenuse. Cosine, SOHCAHTOA, is the trig relationship between adjacent and hypotenuse. The cosine of this angle theta which is the angle that the little sister's swing makes with the vertical at the end of part A, is the ratio of the adjacent side divided by the hypotenuse. In this case, 1.43 meters divided by 3.00 meters. I can take the inverse cosine of that ratio. The units cancel. And this tells me inverse cosine of 1.43 divided by 3, enter, is 61.5 degrees. This is something that we covered a year ago in this course. It's something we did not cover this year in this course. So this homework assignment, in a sense, is revealing the difference between what you would have been expected to handle in a classroom and what you've actually experienced by doing everything online. I believe the period ends at 9:05, not 9:07, and I'm way behind in debriefing you on the answers to the homework assignments. But I think you're starting to see that there's material that you hadn't practiced before that showed up on this homework. I'm not crazy about the idea of having this type of questions on your test, which is coming up the next time we meet. But there are some aspects, like from this homework, that I would say, yeah, you should be able to do this or that. I'm going to jump into part B and just leap to the answer. And the reason for that is I do want to kind of get through as much of this as I can in my remaining 7 minutes. For problem 2, part B, Jessica gives her little sister a second push. This time, the force is 230 newtons. The time is 1.20 seconds. If this impulse is added to the other one, what maximum height would she reach? Well, the change in velocity, 230 times 1.2 divided by 33.5, would be 8.24 meters per second. If you add that to her 5.55 meters per second at the end of her first swing, I think you can believe me when I say, whoa. If she really were moving at 13.8 meters per second after the second push, she would go, woo! She would go completely around. This corresponds to a final height over 9 meters. And the top of the swing is only 6 meters high. So in terms of energy, she has enough energy to go over the top of the swing set. Interesting idea. Please don't try it at home. So the problem is a little bit unrealistic. And in part C, they ask, so what's the maximum angle that the swing makes with the vertical? Well, if she really goes, and we're not going to calculate the normal force at the top of the swing, but if she did remain in contact, well, even if she doesn't remain in contact with the swing, her angle is going to be directly above the bottom of the swing. So the answer to part C is 180 degrees. She goes over the top. even if she's not touching the top. She goes over the top of the swing. Okay, I need to now jump into problem 3. A 5.00 gram bullet is fired into a 3.00 kilogram block of wood that is initially at rest. So here comes a bullet. Here comes a block of wood. This is 5 grams, which right away I'm going to tell you is 0.00500 kilograms. And the block had a mass of 3.00 kilograms. The wood slides 75 centimeters. I'm going to convert that to 0.750 meters right away. And the time is 675 milliseconds. So you can see last year I was really trying to have the students work on using the Greek prefixes appropriately. What is the initial velocity of the block? And here you get to use a kinematic equation, because really we have 3 givens: the displacement, the time, the final velocity because it stops, and they're asking for the initial velocity. We assume friction is constant. We assume the acceleration is constant. Hold up your fingers, please. Which one of the 4 kinematic equations of motion connect these 4 variables to each other? 1, 2, 3, or 4? Aw. Wow. Okay, you guys are outdoing your classmates from yesterday. Nice. Okay, fingers down. Peace out, kids. You're right. The second kinematic equation of motion is the one to use. Delta x is 1/2, open parentheses, initial velocity plus final velocity, close parentheses, times time. In this situation, we're interested in what is the initial velocity. I'm just going to jump into it. 2 times 0.75 divided by 0.675, enter, and I get 2.22222222222 meters per second. That would be the answer to part A. Part B. What is the kinetic energy? Well, kinetic energy is 1/2 mv squared. And the mass in this case is the block with the bullet inside of it. So 1/2 of 3.005 kilograms times 2.22 meters per second quantity squared. Beep, beep, beep. And strictly speaking, the mass of the bullet isn't going to change the answer. It's so small. But I'm getting 7.40 joules. So that is the total energy. No, that is the kinetic energy afterwards. All right. Now, I want to point out really quick that this is a perfectly inelastic collision. Kinetic energy is not conserved. So if you tried to calculate the speed of the bullet using conservation of energy, you would fail because work was expended in burrowing a hole into the block of wood. The only way you can get the speed of the bullet is by conservation of momentum. The mass of the block plus wood times the speed of the block plus wood is equal to the mass of the bullet times the initial speed of the bullet. So, anyways, that's the correct way to do part E. The period ends in right now. I'm going to stop recording right now.